Welcome to the first episode of the course dedicated to the ECS Control System V9. This course has been designed to help you master working with the ACESYS V8 library for programming Siemens controllers in the Step 7 environment. It is aimed primarily at intermediate-level individuals who have basic knowledge in networking, programming Siemens PLC controllers, and SCADA visualization systems. This course will introduce you to one of the leading standards in industrial automation. In this episode, we will cover the basic types of workstations in automation systems, configuring the working environment, the hierarchical structure of a project, establishing communication between the simulated PLC controller and the ECS Control System V9 using Step 7, PLCSIM, and NetToPLC software. Software we will be using: Step 7, for programming Siemens PLC controllers using the ACESYS V8 library; FLSmith Workplace, for modifying visualizations in the ECS Control Center V9 system. This course provides an excellent opportunity to enhance your skills in working with automation systems and to understand how different elements, from PLC controllers to SCADA visualization, work together to form complex industrial automation systems. Let's begin by discussing the basic types of workstations in automation systems. In automation systems, we commonly encounter three types of workstations: engineering station, visualization server, and operator stations. Engineering station is where the creation, configuration, and management of the automation system occur. Its primary purpose is to provide a platform for programming PLC controllers, configuring, diagnosing, and maintaining the system, as well as simulating, testing, and uploading programs to the controllers. Visualization server acts as the central hub for managing the entire system. It hosts the process visualization, which clients such as operator stations connect to in order to monitor and control the operation of the system. This centralization of process data, alarm management, and data collection allows for effective oversight and easy management of the system from a single location. Operator stations are computers from which operators connect to the SCADA server to control, manage, and monitor industrial processes. These stations display data and visualizations from the system, enabling operators to manage processes, respond to alarms, and analyze data. The working environment we will use will replicate a real industrial automation system. To achieve this, two virtual machines will be run on a computer using VMware Workstation Pro v17. All machines will be connected to a single local network with static IP addressing. The first virtual machine is the engineering station. This station will be used for programming PLC controllers and will also run the PLC simulation. It has three key tools installed: Step 7, version 5.7, tool for programming Siemens PLC controllers; PLCSIM, software for simulating the operation of a real PLC controller, allowing testing of programs without needing a physical controller; NetToPLCSim, software that simulates the connection between the PLC controller and the network as if the simulated controller were a real device on the industrial network, enabling communication with the ECS system. This virtual machine has two network interfaces: PLCs 192.168.1.30, network card responsible for communication with the simulated PLC controller; terminals 192.168.1.20, network card used for communication between the engineering station and the ECS server, as well as other network components. The second virtual machine functions as the ECS Engineering Control System Visualization Server. It will run the visualization of our process and also has FLSmith Workplace software installed for modifying the visualization. The ECS server has one network interface: terminals 192.168.1.10, network card enabling communication with the engineering machine, data exchange with the simulated PLC controller, and connection to the operator station. The computer running these two virtual machines will also act as an operator station. This setup will allow us to view the process from the perspective of an operator during later stages of the course. The operator station will have one network interface: Ethernet 2, 192.168.1.1, network card allowing communication with the ECS visualization server. Let's take a look at how this working environment is configured. First, let's check the network card configuration on the host computer, where two virtual machines are running. To do this, we need to open the network card properties. As you can see, The host's network card is set to the address 192.168.1.1. On this computer, two virtual machines are running. Client ECS, a virtual machine serving as the engineering station, and server ECS, a virtual machine acting as the visualization server. On the client ECS machine, we have installed Step 7, PLCSIM, and NetToPLC. Let's now check how the network cards of this machine are configured. It has two network cards, one labeled PLCs with the address 192.168.1.30 and the other labeled terminals with the address 192.168.1.20. Both virtual machines have their network cards configured in bridge connection mode. This works as if all virtual machines and the host computer were connected to a single shared switch in the local network LAN. On the second virtual machine, server ECS, the ECS server is running with the FLSmith workplace software installed. It is from this interface that we will be able to make changes to the SCADA system. If we now access the network interface, we can see that the ECS server has the address 192.168.1.10. Here as well, the network card is configured as a bridge connection. For diagnostics, to check if all machines are on the network, it's useful to use the ping command in the command prompt to verify that all network cards respond. As we can see, all the network cards respond, meaning all devices are within the same network. During this course, we will use a pre-prepared project template. This template includes the imported ACESYS V8 library for Siemens Step 7, as well as a pre-configured hardware setup for the controller and a project structure that adheres to the standards of this library. To access the project template and other materials, please contact us at automationmindsinfo@gmail.com. Let's start by opening the project. Click on the Somatic Manager icon, then select File and Open and choose the project file. The project contains a controller named S1PLC1. Select it and proceed to the hardware configuration settings. Now let's examine the configuration of the individual components on Rack 0. On slot 1 is the power supply, and on slot 3 is the Central Processing Unit CPU S746-2DP. Indicating that we are working with a controller from the S7400 family, equipped with two Profibus interfaces. Interface X1 has address 2, while X2 has address 3. On slot 4 is the network module CP4431, which has one network card X1 with two ports, P1 and P2, and this network card is assigned IP address 192.1.40. On slot 5 is a module with 32 digital inputs, and on slot 6 is a module with 32 digital outputs. Additionally, the hardware configuration of the controller includes a distributed I/O island ET200M, which communicates with the PLC controller via Profibus and has address 4. This distributed I/O island includes 3 cards with 16 digital inputs each, 3 cards with 16 digital outputs each, 1 card with 8 analog inputs, and 1 card with 8 analog outputs. This hardware configuration of the controller enables the programming of a wide range of interesting industrial processes. Before we begin programming, it is essential to understand how the project structure is organized within the ACESYS V8 library. This library is designed based on a functional hierarchical structure, which works exceptionally well in complex industrial processes, such as those found in the cement or mining industries. The hierarchical system allows for seamless exchange of commands and statuses between parent and child objects, significantly simplifying process management. At the top of this hierarchy is the department, which represents a larger section of the process, such as the entire raw material transport system. The department consists of smaller components, known as groups, which manage the logical operations and control sequences within the department. Each group controls units, individual devices or subsystems, such as unomotors, gates, valves, and may also include other elements like PID controllers, totalizers, selectors, analog, alarms, and many others. Units may have additional components assigned to them, such as alarms or analog measurements. For example, in the case of a drive controlled by a frequency converter, any alarms related to converter faults, as well as status data, will be assigned directly to that drive unit. This ensures that information about the status of each device is easily accessible, and any malfunctions can be precisely localized. To better illustrate how this structure operates, let's look at an example of a raw material transport system to silos. Such a system might be represented by one department consisting of several groups. For instance, Group 1 manages transport to Silo 1, Group 2 manages transport to Silo 2, and so on. Each group contains a set of operational units, such as unimotors, gates, valves, along with alarms and analog signals. Some units may include alarms, analogs, and other elements if they directly relate to a specific piece of equipment. This hierarchical structure not only facilitates easier programming and system configuration, but also ensures effective management of the entire process. It allows for quick and accurate fault diagnosis, complete control over the status of individual devices, and maintains consistency across groups and departments. This organization enables efficient control of complex industrial processes while preserving flexibility and control at every level. Before we dive into the details of our program, I'd like to share a simple trick that can significantly improve your comfort during long work sessions. I personally often use dark mode to reduce eye strain. You can activate it using the magnifier tool. Simply open the settings, go to Color Filter, and check the Invert Colors option. This will invert the colors on your screen, making the background in the Step 7 environment black. Trust me, after a few hours of work, your eyes will thank you for this adjustment. Now, let's move on to discuss the hierarchical structure of our project. First, open the project and expand the S1PLC1 tree. Then, expand the CPU 46-2DP and the controller S1PLC1 and click on the Blocks tab. To get a clearer view of the block structure, I recommend clicking on Details. In this view, you'll see many functions and blocks, but most of them come from the ACESYS V8 library. In the ACESYS standard, each element of the system is implemented as a separate FC function, which calls the appropriate FB function block. Let's look at an example. Open the FC1001 function, which corresponds to Department A1 DEP01. In this function, the block FB201 from the ACESYS library is called, specifically ACESYS DEPT. At first glance, this might seem a bit complex, but let's focus on understanding how the program's hierarchy works. We can see that in the department function FC1001, there is a call to a group that belongs to this department, namely FC1501 A1 GRP01. If we right-click on this call and select Called Block and then Open, the contents of that function will open. Here, we see a similar pattern. Within FC1501, the FB202 function block is called, which is ACESYS Group from the ACESYS library, because we are now inside the group function. As we scroll down, we see that the group contains elements such as selectors, alarms, analog signals, and units. Delving deeper into the hierarchy, we can open one of the drive functions, for example, FC4001, which is responsible for a specific drive. In this function, the block FB210 ACES motor is called. This function can also call additional elements of the drive, such as alarms, analog signals, or selectors. In summary, the ACESYS library is based on a hierarchical structure. Each system element consists of an FC function, which calls the appropriate FB function block from the ACESYS library, depending on what the object represents. This organization greatly simplifies managing complex industrial processes, allowing for clear separation of responsibilities and ensuring full control at every level of the system. When working on a project in the ECS system, a crucial first step is to create a so-called solution. To do this, you need to access the server and open the FLSmith Workplace application, where you can make modifications to the ECS system. A solution serves as a container within the ECS system for all project elements. This allows for easy project management, backup creation, and quick restoration if needed. To create a new solution, go to the System tab, expand the configuration list, and select HMI Editor. A message will appear indicating that the operations station will be closed. Confirm this by clicking Yes. Then click on New Solution. For this course, we are focusing on a project related to the Transportation Department, which will be organized as Department A1. Therefore, enter A1 in the Solution Name field, select Transport as the source name, and set the source version to 0.0. When you expand the list, you will see the solution you have added. It is crucial that all elements we create for this project are associated with this solution so that the entire system can be backed up and restored with a single click. Once the solution is created, we can proceed to add our PLC, Programmable Logic Controller, to the project. For this, go to the System tab, then navigate to Communication, I/O Editors, and Diagnostics. The ECS system supports connections with various PLC manufacturers, but we will be using a Siemens PLC, so open the Siemens section. Right-click on PLCs and select New. This will open a window where we can configure our PLC. First, we need to assign the appropriate solution. Select the previously created A1, which ensures that the PLC will be restored along with the system if needed. In our project, the PLC will be named S1 PLC1 and will be assigned PLC number 1. Since we are using a Siemens S7400 PLC in this simulation, leave the PLC type as Siemens S7. The ECS system also supports newer PLCs, such as the S7-1500 series, in which case you would choose Siemens S71X. However, we will stick with Siemens S7. Communication with the PLC will occur via TCP/IP, so select TCP/IP as the network type. Enter the PLC address, which in our case is the same as the network card address of the PLCs on the engineering station, 192.168.1.30, not the address configured in the hardware of the PLC. Check the Block Support option and click OK to add the PLC. After adding the PLC, click on it to proceed with further configuration. In the General tab, select the Active option, which means that the connection between the PLC and the ECS system will be active. Next, configure the Watchdog, which is a simple mechanism for monitoring the connection between the visualization system and the PLC. Set the Watchdog period to 10 seconds, meaning that if the monitored bit does not change for 10 seconds, it will trigger an alarm indicating a communication failure between the visualization system and the PLC. The variable to reference is located in the MasterDB block. Let's go to the engineering station, open MasterDB, in our case DB1000, and find the variable named Watchdog HMI. It is located at word 22. Return to the configuration and properly set up the watchdog. Configure the type as DB, 8-bit, block as 1000, word as 22, and bit as 0. Next, configure the rack and slot. Go back to the hardware configuration. On the engineering station, click on S1 PLC1 and then Hardware. We see that our PLC is located on rack 0 and slot 3, so configure these settings in the ECS system accordingly. Enter rack 0 and slot 3. Leave the remaining tabs unchanged for now and save the changes by clicking the Save icon in the top left corner. Once we have added the PLC controller to the project in the ECS system, the next step is to start the simulation. We begin at the engineering station, and the first thing we need to do is launch the NetToPLCsim program. After starting it, we will see a message indicating that the application is intercepting communication on port 102. This port is important because it handles data exchange between the ECS system and the Siemens PLC controller. NetToPLCsim intercepts, translates, and redirects this data to the PLCSIM simulator. It works both ways. When PLCSIM needs to send data back to ECS or SCADA, NetToPLCsim also mediates this communication, again using port 102. Once NetPLCsim is running, we proceed to work with PLCSIM. We open the project and click the PLCSIM off icon on the toolbar. A new window will open where we will see our simulated controller and its current operating mode. At this stage, we need to upload the program to the controller. We do this by selecting the controller and pressing the Download button. A prompt will appear asking if we want to overwrite the system files. We confirm this by clicking Yes. After the program is uploaded, the controller will be in stop mode, which will be visible in the simulation window. Now, we need to start the controller. To do this, we switch the controller to Run P mode, Run in Programming, which means the controller will execute the program, but we can also continue programming and making changes. The next step is to configure the server in NetToPLCsim. we click the Add button and a configuration window will open. The first thing we need to enter is the name. It's best to use the name corresponding to the PLC controller's name, in our case S1 PLC1. Then, we set the IP address of the network card where we want to redirect the network traffic. In our case, it will be the IP address of the PLC's network card, 192.168.1.30. Next, we select the IP address of the simulated PLC controller that we want to connect to the real network. Remember, in the hardware configuration, we set the network card address of the PLC controller to 192.168.1.40. We then set the rack and slot, also according to the hardware configuration, so we set rack to 0 and slot to 3. We confirm these settings, select the server from the list, and start it by clicking Start. Finally, it's worth checking if communication in the ECS system has been established correctly. Let's head over to the ECS server. If a green circle appears next to our controller in ECS, it means everything is working properly and the simulation is running and ready to go. Since understanding how to establish communication between a PLC and the visualization system is crucial, let's walk through the process again to clearly illustrate how it works. The server with IP address 192.168.1.10 communicates with the network card of the engineering station at 192.168.1.30 as if it were directly connected to a real PLC using port 102. On the engineering station side, the NetToPLCsim server is running and listening on this port. When it detects incoming communication, it forwards the data to the simulated PLC with IP address 192.168.40. The PLC responds to the request, and the data is sent back to NetToPLCsim, which then redirects the response back to the network card at 192.168.1.30 via port 102. Finally, this information is returned to the ECS system. It's important to note that the ECS system only sees the network interface, which in this case is the network card at 192.168.1.30, the PLC's network card, and not the simulated PLCSIM itself. This is why, when configuring the ECS server, we specify the address of the network card and not the IP address 192.168.0.40 of the simulated PLC, which is set in its hardware configuration. I hope everything is now clear when it comes to setting up a PLC simulation using NetToPLCsim and PLCSIM. In this episode, that's all for now. We learned about the basic types of workstations in automation systems and how to configure network connections between them, illustrated with a real-world example. We understood how the hierarchical project structure in the ACESYS V8 library is built and how to simulate a PLC and establish a connection with the ECS system. If you enjoyed this episode, support us in creating more videos. Leave a like, subscribe, or consider financially supporting our channel. Remember, every bit of help motivates us to create new content. At the end, there will be a few questions related to this episode. Test your knowledge and see if you can answer them.